Okay, so this is just a quick little presentation, just introducing what this topic is and why it's important. And so I'm going to just discuss what I mean by multi-phase combustion and the combustion of energetic materials. So I guess first things first, why study multi-phase combustion and energetic materials? Well, multi-phase combustion is important for a lot of things. Diesel engines, and tractor trailers and other things like that use the combustion of fuel sprays. And so quite clearly that is important for diesel. Understanding multi-phase combustion is important to making new efficient diesel engines, which can not only be higher performing and more fuel efficient, but can also lead to reduced pollutant emissions. Now, the formation of pollutants is something that we're not going to discuss in this class. Multi-phase combustion is used in liquid fueled rockets, like in the old solid rocket boosters. They used liquid oxygen and hydrogen as the fuel. The SpaceX rockets, I believe they use, is it liquid methane or is it liquid kerosene? I can't remember. I'm not a SpaceX nerd. And then they use LOX as their oxidizer. And so there's a lot of modern rockets that basically use liquid fuels. And so you need to basically atomize those fuels into a bunch of little droplets and then basically burn that. Coal combustors, even though they're being phased out due to pollutant emissions from coals, but it's a big part of everyday life. And also explosion safety. And so here I'll play a little movie, if you can see it, just to show that basically mixtures of innocuous particles can oxidize with air to produce explosions.
A simple explosion requires 3 essential ingredients: a means of ignition, a fuel source, and oxygen to support the rapid combustion, which, if confined, will produce an explosion.
That's flour on that piece of paper.
Well, there we have a very elementary.
So what he did there was he took a candle and basically lit it. That was the ignition source. Then he put some sort of tube around it that added confinement. Then from the top, he took some he took a pile of flour and then dumped it in from the top. Then what happened is the flour fell to the bottom, and as it fell to the bottom, it sort of dispersed and mixed nicely with the air. Then when the flour fell down to the bottom and then hit the candle, it then basically exploded and then blew up, as you could tell by the sound. And while this is sort of a nice, cute example, these explosions occur with basically devastating consequences in all sorts of coal mines, sugar refineries, grain silos, things like that, all the time. And then, so even particles that you would normally not think of burning, such as flour, can produce explosions. And basically, we will be going over some of that in this class. And another video that I will show will be, if any of you were a bit of pyros when you were kids and you played with WD40 torches. I know some of you know what I'm talking about, like, don't be shy. So if you take a lighter and take a can of WD40, which is just, if some of you don't know what that is, that's just a spray-based lubricant like to fix a squeaky chair or something like that. So, but you can actually make a torch from that. And as long as you don't let go of the spray nozzle, it will be self-propagating. Now, if you look at this, you may be thinking he's insane and he's going to kill himself. And I'm not condoning this. I'm not condoning you guys doing this, because I don't want you guys to get burned. But I used to do this as a kid, and my mom would catch me, and she'd be like, she would tell me that you're going to blow up the can of WD-40. And the answer, now that I'm a combustion guy, I know that that is impossible. It is impossible for the flame, which is right here, to chase all the way back into the spray nozzle, because here it's pure fuel. There's just no oxidizer. There's no air for it to basically go and to basically chase down into the can and then basically blow it up. But here we see basically this is a spray flame. So here we have a spray of fuel droplets. That's in the form of WD-40, whatever material that is, I have no idea. And so these are a sort of mist of very fine droplets. You have an ignition source here. And actually after it's ignited like this, he could actually move his hand away and it'd be self-propagating. And you have the actual ignition point of the spray flame right here. And it's sort of chasing back along the sort of upper edge of this. And this upper edge is basically where that mist of WD-40 droplets and air are basically stoichiometrically or perfectly mixed. And so this is a classic structure of a spray flame right here. And so we will be discussing spray flames a little bit in this class. They are extremely complicated. And so we will not be getting into them into too much detail. But it's just sort of an interesting sort of side effect of this stuff. And so, and I guess the multi-phase combustion considers the combustion of droplets, sprays, and particles and particle clouds. Okay, so are there any questions on that? Any untoward stories of like when you were a kid of doing stuff that you weren't supposed to do? Okay, so now we discussed multi-phase combustion and what is meant by that. So a lot of you may be wondering, what is an energetic material? Now, in the previous combustion class and even that spray flame, the fuel and oxidizer were basically two separate molecules. And for the burning to occur, the fuel molecules and the oxidizer molecules, oxygen in this case, they needed to actually collide and basically bump into one another. And if the configuration if the orientation of the fuel molecule and the oxygen molecule is appropriate, and there's enough kinetic energy in that collision, then basically those two molecules will basically react and produce little fragments, and then those fragments would be combustion products. Now, so even if the oxygen and the fuel molecules are pre-mixed, that is, you don't need any external mixing. At the molecular level, they are not pre-mixed. Is that you still need a collision between two different molecules. But an energetic material, on the other hand, is a compound where the fuel atoms and the oxidizer atoms are present in the exact same molecule. So here is the TNT molecule. These black molecules are carbon. The white molecules are hydrogen. The blue molecules are nitrogen. And the red molecules are oxygen. And so you could sort of see this structure here is really a remnant of a benzene ring. It's a fuel-rich structure containing carbon and hydrogen. And basically, how they made this was they basically cleaved off some of the hydrogen bonds and replaced it with a structure called and replaced it with this NO2 structure. And now this NO2 structure, it contains 2 oxygen molecules, and it's sort of separated from the carbon and hydrogen molecules by this nitrogen, basically by this nitrogen atom. And so this nitrogen atom sort of keeps the oxidizer atoms and the fuel atoms nice and separated, and so that at low temperatures they don't just spontaneously react and burn and do crazy things. But at high temperatures, when we discuss the chemical reaction pathways, is that the first bond to go is that basically as this starts to react, is the first bond to be cleaved is this bond right here. And so you have this free NO2 molecule and this remnant here. And then now the oxidizer molecule and the fuel molecule are separate things, and then they can basically, you can get the oxygen atoms in contact with the fuel atoms, and then they will basically burn. And an amazing thing about these is that they will burn by themselves with no oxidizer. Okay, so they do not need oxidizer. Now, to burn completely, they may need additional oxidizer, but they will still burn by themselves. Is that they are called energetic materials because they add energy to the system, and so that their chemical reaction is always exothermic. And energetic materials are used for explosives, rocket propellants all the time, and also pyrotechnics. Fireworks are an example of an energetic material. The sort of pyrotechnics that you see at a big concert, those use energetic materials. And there's all sorts of these things. This here was a TNT molecule. That's basically extremely fuel rich, and we'll discuss that probably on Wednesday. And just to show how they burn, here is an old movie. This here is a crystal of ammonium perchlorate. It's an energetic material, and they ignited it from the top, and you'll see a flame being chased down from the top to the bottom.
Ammonium perchlorate. This
here is a classic propellant flame.
Temperature and pressure.
And we will be discussing in detail how these energetic materials burn like this.
Ammonium perchlorate. This film reviews several reactions of ammonium perchlorate to temperature and pressure.
Okay, and in fact, your computer project, or actually one of them, is to do a one-dimensional model of this flame structure right here. So all this little turbulence and stuff, it won't get that, but the distribution of the chemical species and temperature, things like that, on the gas phase side of this interface will be discussed. And also you can see here, there's a nice clean interface between the ammonium perchlorate, that's a solid crystal, and the gas. And so that's why we're going to spend some time to discuss how you treat the boundary conditions at an interface like this. Because if you want to model this, you need to know what to do with this interface. So it's not just all pure gas. Okay, and then here's another, where's RDX? Here's another example. Now, ammonium perchlorate is actually, we will not be modeling that. It's actually, there's a lot of unknown mysteries as to some oddities with modeling ammonium perchlorate that we will not get into. But here is a crystal, it's called RDX. So here is a crystal of RDX, or a pellet of it that's pressed. They got it in a cup, and then that's also an energetic material that's commonly used in modern propellants and explosives. And so they ignited it, and you can just see it burning down. And if you look carefully here, I don't know if the video is clear enough for you to see this, but you see a flame here that's being chased down into the cup. And below my pointer here, you have the clean, neat RDX, pressed RDX pellet here. And between here and the flame, you actually have what's called a foam layer. Is that that if the movie plays cleanly, you'll see all these little bubbles and things like that. And so the structure, not only in the flame on the gas phase side where the actual chemical reactions are occurring, but also within the solid itself, there are really complex phase change processes, a bubble formation, things like that. So it's really, really complicated, but that's what makes it interesting. Now, in your 1D model, you will not be accounting for all those bubbles. That was somebody's PhD thesis like 10 years ago. I can't expect you to do to model all that detail in a class project. I may be crazy, but I'm not that crazy. And so those are classic energetic materials, but there might be some things that burn that you would normally not think of. So here is, these are experiments. So this is a mixture of aluminum particles, or nano aluminum particles, and water. And aluminum particles, basically metals you'll learn in this class, are very good fuels, very energetic, extremely energetic. And they burn not only with air, or really oxygen, I should say, though they will burn with water very efficiently. So what Rich Yetter and Steve Sun did was they took nano aluminum particles, that is, their particle diameter is on the order of 10 to 100 nanometers, and they mixed it with some water such that the equivalence ratio, that is the amount of mixing between the oxidizer, water in this case, and the fuel, aluminum particles, is perfect. So there's the perfect amount of oxidizer to burn all of the fuel with no excess water or no excess aluminum particles. And so if you play the movie here, they are just looking at this as to, and then they basically take it and they put it in a little test tube, and they basically burn it from the top down, and they're seeing how fast this burns. And so that's this RB, that's called a burning rate. And they're looking at the effect of pressure. They were sort of studying this to see as sort of interesting rocket fuel. And so they ignite it from the top, and you can see that in this mixture of aluminum particles and water, it's nothing but aluminum particles and water. You see this nice flame basically propagating down into the tube. And so how fast it's propagating down, that's called a burning rate. And you can see that that burning rate is a pretty strong function of pressure. And so there's all sorts of interesting oddities and things that you normally would not think of that can burn. And also we'll be going over things, an issue called convective burning. So here is, when I took a similar class back in the day, they had labs to do this. So we had demo day. And so we had and so we had some fun. Anyways, so the instructor took a piece of yarn, they made a slurry with black powder and water, and basically coated the piece of yarn with black powder and basically made a fuse. And then you're just looking at the effect of confinement, and he confined it with just this really loose garbage paper towel. And so what do you think will happen when he ignites the fuse from the end here and it goes into the paper towel? The flame will take off, will propagate much faster. And so I'll play the movie. It's hard to see because there is so much smoke, but if you look very carefully, you'll see in the beginning, the flame propagates slow, and then it gets into this sort of paper towel here, and then it just sort of takes off much, much faster. And so what's happening there, and you think, well, what's going on there? I mean, why is a paper towel confining? It's a paper towel. Why is it confining? Why is it producing that with the flame? Well, the issue that what is occurring is something called convective burning. So you need to remember, because this black powder that is coating the piece of yarn is burning by itself. And so even though it's weak, this paper towel is actually forcing some of those combustion products to actually propagate further into this, like basically like A2. And then those hot combustion products are then heating up the black powder on the outside and basically preheating it. And so the flame accelerates once it gets into here because of that convective heating effect. And that's why this is called convective burning. Typically in rocket and combustion systems, you avoid this basically very, very much because this can cause explosions. Okay, and then what else? Oh, and we also, just a nice interesting aside, he repeated the experiment, but instead of confining it with a paper towel, he used a better confiner, which was tape. So again, not a very strong confiner, just tape. So the effective confinement can have a pretty huge impact. And also, we'll be discussing a little bit when we get into the multi-phase aspects, the combustion of thermites. Again, we'll be just discussing these at a sort of 6,000 foot elevation level. And so here he has, it's not there anymore. So here he has a pile of a mixture of nano aluminum and molybdenum, I can never say that word, molybdenum trioxide. And that is an extremely reactive mixture, and that's called a thermite. And molybdenum, and essentially the aluminum is so reactive, it will basically rob the oxygen molecules from the moly trioxide. And it's extremely reactive. And this doesn't produce gas. The only combustion products are liquid aluminum oxide and pure molybdenum. I can never say that word. And this is extremely reactive. Oh. And it didn't generate gas, or at least not that much gas. And so most of that shock that you heard was produced from just very rapid heating. Now, to produce a good explosive, you normally want a very strong gas generator to basically take the volume of that solid and turn it into high temperature, high pressure gas. And then the conversion to gas will produce the large majority of blast overpressure and things like that. Okay, and just to show, we'll be discussing a little bit about when things go wrong. There's a phenomenon called Cookoff. And so if any of you are familiar with, there was an explosion at Pepcon Henderson. They made the fuel for the solid rocket boosters for the space shuttle program back in the day. And there was a fire in their plant. And so all this stuff here is ammonium perchlorate and other rocket fuel components. And so what happens when you subject a large quantity of energetic materials to heating for a very long time is a phenomenon called Cookoff. And Cookoff is sort of when you slowly heat it and it's sort of, it isn't quite correct, but it all ignites at the same time and it basically blows up. And Cookoff is responsible for a lot of accidents. That's sort of why if you are on a Navy destroyer or something like that and there's a fire, it's a very, very, very bad deal, not just because of the fire in the ship and the crewmates, but you do not want to get the fire anywhere near anywhere near the artillery because it can cook off and it can blow up. And it's this one, luckily this occurred early in the morning, so nobody was there. So I don't think this one killed anybody. It did produce lots of damage though. And when you watch the movie, you can see the nice sort of spherical shockwave propagate out. And there's an interesting story is that why this video was so good was some electrical linemen were basically working on a power line and they're making a video to basically teach younger linemen how to actually, you know, basically like fix power lines and things like that. And the tower that they were working on just happened to overlook this Pepcon Henderson. And so there are videos flying around the net where that basically have the audio where they're just sort of marveling what's going on. And then they see the shockwave, basically, they see the shockwave propagating towards them. And then they make the comment, this is going to be loud. Cover their ears. So that's sort of why this is actually a very, for the time, a very well shot video, because they had a professional camera crew there actually making how-to videos. So that was really sort of interesting. So that's just some of the aspects of this and some of the aspects of what we will be going over in this class. Are there any questions and comments? Okay, and then also the projects, I'll probably make them group because these will be a bit more involved than the ones earlier. This is a small class, so you know, a group project, and I don't know how many. We'll see we'll see when the number of students stabilize with this class as to how many people there will be per group. And so, so are there any questions with this? So we might as well get going. And also, if you looked on Canvas, I do have these slides available for you to look at. And so the slides, I'll be giving sort of slide presentations when it makes sense. I'll do derivations on my iPad when it makes sense to do so. And then I will also post some videos when it makes sense, like to show Cantera, because I know I'm not going to spend too much lecture time or actually any lecture time at all discussing Cantera. But I know not all of you have experience with Cantera, so to mitigate that, I'll be making some videos as to how to use Cantera. And so for those of you who have already had Cantera and know how to use it, you can use those to refresh. And for those of you who have never used it, there will be a nice introduction. Okay, and so this will be we got 5 minutes left, might as well get going. So so this here is part one. So here we're going to start the review, and so we'll start with the thermochemistry, and here we'll just go over part one. Will just be the basic definitions, and so we're going to review what mass and mole fractions are. We got to start at the beginning: air-fuel ratio, equivalence ratio, complete combustion. Basically, what is meant by that? Mixtures of ideal gases, and we'll be extending this to mixtures of real gases because that's becoming important in modern combustion theory. Okay, so what we will be discussing on Wednesday, or what we'll be basically working towards for the first week, is basically this canonical problem here. So consider we have a closed tank. It could be fixed volume, or a tank that has fixed pressure where we have sort of a stack of weights on it. And it contains a mixture of fuel and oxidizer at some temperature, pressure, density, and volume. And it starts out at that pressure, temperature, and etc. So for example, this fuel could be methane and the oxidizer could be air. So really what we want to find here is the final thermodynamic state, assuming that the fuel and oxidizer can ignite and burn. And so what is the final pressure? What is the final temperature? And also what is the final composition of the products? Is it pure CO2 and H2O, or is it a mixture of some other things? And so basically we will be discussing that, and then adding what is the influence of non-ideal equations of state? Because again, that's becoming important in modern combustion. Okay, and so basically we'll be working towards that. And so we got to start at the basics to define what is a chemical species. And a chemical species is really any molecule, atom, ion, etc., that is undergoing a chemical process or measurement. And so air by volume is a mixture of different gases, and each one of those gases is a species. So air is about 78% nitrogen by volume and about 20.5% oxygen by volume. Okay, and basically each one of these components is a species. Okay, and now for combustion purposes, we basically take all of these additional species such as CO2, argon, etc., and basically lump it in with the nitrogen. And we approximate air as a mixture of 79% nitrogen and 21% oxygen by volume. Okay, so that's pretty, so basically you can think of all the species as all the different little chemical component or the different molecules that make up a mixture of gases. Okay, and then basically using that, there's a parameter called mole fraction and mass fraction. Mole fraction is X sub I, and mass fraction is Y sub I, and I is referring to species. So that could, so I could be O2, N2, CO2, things like that. And the mole fraction is really just the number of moles of species I divided by the total number of moles of the mixture. So basically, you take the number of moles of, if you want the mole fraction of oxygen, you take the number of moles of oxygen and divide it by the number of moles of oxygen plus the number of moles of nitrogen, et cetera, et cetera, et cetera. Okay, and so so this here is just a basic definition, and this holds for real gases and ideal gases. Now note, this is important for mixtures of ideal gases and ideal gases only. Volume fraction and mole fraction are equivalent. They are the same thing. I'm not going to prove that in this class. I did in the previous combustion class, but just take note that that is only for mixtures of ideal gases. If you use a real gas equation to state, or you have particles in the mixture, that is no longer true. And then similarly, there's something called mass fraction, which is Y sub I. And in the explosive lit, you actually see that as lambda, but I'm going to use traditional combustion nomenclature and call that Y. And the mass fraction is just the masses of the ice species divided by the total mass of the mixture. Okay, and so we will be discussing the relationship between mole fraction and mass fraction on Wednesday, and also note, by definition, the mass fractions and mole fractions must sum to unity. So